the distance for this one is 2. The distance from 4 to 2 to 2 is 2, in this case 2, am I right? 4, 2 plus, let me see, 4, 2, 4 2 is 2, right? So this let me just make 2. And then you also do the computations for cluster 2 for each point to the cluster centroid again using L1 norm. L1 norm is easier to compute. That's why I provided L1 norm. Okay, you take the difference and add them up. Take the difference, add them up, and then you get 16. If you make a mistake in one of them or two of them, when you adding up, it's not a big problem. But I need to see that you are doing the operations correctly. That's the main point. In the test, those type of mistakes are possible. You know? There are meaningful errors. Okay? But if you put the data into incorrect clusters, then there is a problem. Okay? Then that's something that you should be a little bit more careful. Any questions on question 1?
And just about this reconstruction error.
Reconstruction error? Yes. So what we do is, you need to compute the distance of each point to its centroid. So what is the centroid for this data point is 2, 2. How do you compute the distance? So if it's like 2, 2, I write it, and this is 0, 2, okay? Look at the difference for each of them. I get 2 and 0. So the distance is 2 for the first one. For 4, 2, 2, 2, and 4, 2, if you look at the differences, we have 2 plus 0, again 2. So that's, I have 2 plus 2 for the first cluster. Then if I continue with the second one, so the second centroid is 1.75 to 5.7, 1.7, 57.5. First point is 0, the second point 4. If you take the difference, 1.75 plus 1.75, you get 3.5. Does it make sense? So this, I just showed the first operation. And you should do the same thing for each point in the cluster. Why do you compute reconstruction error?
To know the one that has the biggest error.
What is it?
To know the clusters that has the biggest error.
Yes, sometimes you apply k-means multiple times as an example. Let's consider k-means. You start with multiple centroids, right? You can start with 0, 2, 0, 4. You may also start with another initial centroids, and you get different. You may get different results at the end. How do you know which one is better? So to determine that, you may use reconstruction error. Okay. Any other questions on question number 1? So don't write on the papers. Okay? If you have objections, you need to return back to them, otherwise you may keep it. I also provided the formula. I don't know how much it was helpful, but you know, it's there. The other question is density-based clustering. This was the second question. So what you do is, I provide that rate is 4.1 and minimum epsilon points is 3. Okay. So for each data point, you should look at the number of points in the neighborhood, right? So how many of them are less than 4.1? That's what you should look at. So for the first one, I see 2 here, I see 4 here, so there are 2 points. So if it's a 0.04 and 4.2 are the points. In the second one, or second row, 0.4, this one, and this one. So I have 3 points less than 4.1, and for this one, I have this one and this one. I have 2. For the third one, I have this one and this one less than 4.1. and then in this row I have this one, this one, this one. I have 3 less than 4.1, and then in the last one I don't have anything. So you get 2, 3, 2, 2, 3, 0. We typically don't count the point itself. Okay, so if you count the point itself, I didn't cut points, but you need to be consistent. If you count the point in one station and if you don't count in another one, then you are missing something. Okay, that's how I interpret it. So list the core points. So we should find the ones that are 3 or more. That's what core points. So 0, 4 and 3, 4 are the core points. And for the other points, we should look at whether they are in the neighborhood of the core point. So let's check 0, 2. 0, 2, if you look at it's 2, it is in the neighborhood of 0, 4, right? So that's the core point. And let's check the other one, 1, 6. 1, 6 is in the neighborhood of the 0, 4 again. It's a it's a border point in that case. And then 4, 2. 4, 2 is 6 for this one. It is not in the neighborhood of this one. Let's look at the other core point. Other core point is 3, 4. If you look at this one, and 1, 6 is in the neighborhood of 3, 4, so it is a border point. So a border point must be in the neighborhood of a core point. It is not a core point, but it must be in the neighborhood of a core point. And the only point that is not in the neighborhood is 3, 9, so it is a noise point. Any questions? So for the last part is clustering. Okay, clustering. So we start with the core points. Core points are 0, 4 and 3, 4. So I start with labeling 0, 4 as 1. Okay, just cluster 1. That's what I'm going to do. I'm just going to put 1 here. Anything in this neighborhood will be in the cluster. It's in the cluster, in the same cluster. Okay, so these are all in the same cluster. So meaning that 0, 2, 0, 1, 6, and 3, 4 are in the same clusters. Okay. So they are all 1. Then I continue with the other core point. I look at that. I already labeled 3, 4 as 1. I already labeled it here, right? So you said I label it as 1. So anything in this neighborhood is also 1. 3, these will be 1 as well. So all of them go into one cluster, except the noise point. Did you understand this? No? Yes? So you label the first core point. Anything in this neighborhood is in the same cluster. So you continue with the next point. Anything in this neighborhood is in the same cluster. Okay? That's the way we work with density-based clustering. Noise points are not assigned to any cluster. Only core points and border points have cluster assignment. Questions? No? Okay, you are all good. Okay. Third one is hierarchical cluster. Okay, and I say use complete link max. Okay, so what does it mean using complete max? Okay. Normally we can measure the distance between data points. It's easy. You have 2 points, find the distance x, just measure the distance between them, you measure it. Okay? So this is typical. But when you need to find the similarity or distance between clusters. Let's say I have one cluster 1, I have another cluster. This is cluster 1, cluster 2. The cluster 1 and cluster 2 has multiple points, right? They do not have to be the 1 point. Okay. So how how do you find the distance between two clusters? So that is the problem that we should solve. If you use, let me change the color, the closest 2 points between two clusters, assume that the similarity or distance between the two clusters is based on the distance between the two closest points into it. That is called mean. It's called mean. But it could be noisy. The clusters could be too big, right? So we may not always rely on the closest 2 points. To make sure, rather than considering the closest 2 points, you consider the farthest 2 points. Okay? So let me choose another color here. Choose blue, not choose. Let me choose purple. So what are the farthest points here? Maybe this is the farthest 2 points. Okay? So if you pick the two farthest points, that becomes a distance. So this is called max or complete length. That's why it assumes that it covers basically every point. Every distance is smaller than that value. That's what it means basically. So that's max coverage. But when you merge two clusters in hierarchy, you always merge the two closest clusters, but you use max for measuring distances. Okay? You always merge the two clusters. So let's look into this problem now. Initially, each data point is a cluster. We start with single points. So you are going to look at this matrix. We are going to find out the lowest value. What is the lowest value that you see here in this matrix? 2. So you need to find where are 2 is 1 here. Okay. Do we have another 2? No. So I am going to merge 0, 2 and 0, 4. So that's going to be my first cluster. So I merge 0, 2, 0, 4 and 0, 2. Okay. That's the way I'm going to do it. The second thing is I am going to look at the there is no other 2. Okay. So I know it. I'm going to look at the second lowest value in the matrix. What is it? I have 3 here, okay? I have 3 here. I have 3 here, okay? So I have this one, but this is already a cluster. So let me look at it this way. So let me put this as a this way. So it means that this is didn't work. So this is my first cluster. But now, when I want to compute the distance of 1.6 to this cluster, I'm going to pick the maximum. 1.6 to this cluster is 5, not the smallest value. From the distance from 4.2 to this cluster is 6, not 4. Because I have 2 points in the cluster, I'm going to find the farthest distance. Okay? So let me show one of them here so that it makes sense. So my cluster has 0.02 as 1 point, and then the other one is 0.4. And let's say I pick weight 4.2. Okay, this is my other cluster. There's just 1 point. I look at the data points between this. So if I measure 4 to 2 is from 4 to 2 to 0.2, it is 4. The other one is 6. So which one is the maximum one? 6. So I pick 6 as the distance between these two matrices. So that's the way I look at it. Then this one has 3 to 4 to, no, and there are 2 values here. Pick the maximum one, that is 5. And then from this one, 9 to this cluster, it is, the maximum is 10. But I know that in the matrix I have already 3. So I can just merge 4, 2 and 3, 4. That's the next lowest value. I am going to make them another cluster. I just mark it here so that it's easier to visualize. So that's my other cluster now. So if you look at it, so this should be now here I have done it. Okay, that's very good. The next thing is, I have two clusters and then 2 points left. Okay? So what I'm going to do is, this is what we can do. I can compute the distance of these points to each cluster. Okay? So 1.6 is not in any cluster. 39 is not in any cluster so far. So let me compute the distance of 1.6 to the first cluster. It is 5, so it's the maximum of them. For the second cluster, its distance is 7, the maximum of them. So 1.6 is closer to the yellow cluster. 39 is a distance to 10 for the first cluster, 8 to the second cluster. So 1.6 somehow is closer, no, sorry, 1.6 is closer to the first cluster. It is a distance of 5. Okay, 1.6 is closer to 0. So I can merge 1.6 and this first cluster. Okay? Or you could also merge, this is an option here, you could merge 1.6 and 39, but it is a distance of 5. That would be your, in that case, another cluster. So you could go either way in that level, but I pick 1.6. Then you add 1.6 to the first cluster. I'm going to do it that way. Made it. So I want to know the distance between 3, 4, 4, 2, this cluster and this cluster. So 3, 4, 4, 2 is here. So let me mark them here. I need to find its distance to this cluster, the yellow cluster. It's this region. What is the maximum value here? Is 7. The maximum is distance from 4 to 1.6, so this is 7. Then you merge with, finally you only left with one item, and this distance to this cluster is 10. Does it make sense? You always merge the closest clusters. So in a few of the answers, I have seen that merging started with the most distant data points. If you started that way, then it is not the right path, then you automatically lose many points. You always merge the closest point, but the way you measure the distances between clusters is based on max, complete link measure. Okay? That's the way. The other question is, what if hierarchical, at the end you get one cluster, but it's possible that you might be interested in getting multiple clusters. What if you want to get 2 clusters? What with the cluster? What you do is, you cut from here, okay, you cut from here before the last merge. So when you cut it, on one side you have 39, on the other side you have the other data points, so you have 2 clusters that way. So this is what you get. Any questions on this question 3? Question 4, you need to normalize, so you need to do normalization. So I picked these numbers on purpose so that you don't need to do complex operations, but when I look at your answers, many of you did complex normalization, okay? So this is a min-max normalization. The range is 0 to 28, this is the new range, okay? It's a new range. So the first range is 0 to 4, right? This is the first range. What is the second range? It is 2 to 9. Okay, that's the second range. If you look at the range of the values, the first value goes from 0 to 4, the second one is 2 to 9. What you do is, when you map to min-max normalization, if it doesn't start from 0, you need to subtract the mean, okay? So it is x minus x mean, right? So you need to do that operation. Then you need to find the range. The range is, in this case, 7, x max minus x mean, okay? So as an example, if you have a number like, let me see, 4 minus 2 for the second item, I'm looking at the second one, and then the maximum, the range is 7, okay? And then what is the new range? The new range is 28. So to map it to the 28, you need to multiply with 4, right? You need to multiply with 4. So if I summarize, first one times 4, the second one is, no, first one is times 7, second one is x minus 2 times 4. That's what you do for the second one. So if I go this one, 0, 0, 7, 28, 21, 21. That's what I do. For the second one, subtract 0, multiply by 4, 0. Subtract 2, multiply by 4, 8. Subtract 2, multiply by 4, 16. Subtract 2, multiply by 4, 0. Subtract 2, multiply by 4, 8. Subtract 2, multiply by 4, you get 28. Okay? This is how you normalize.
How to get the 4, the multiplication?
4. So this is the times. Let me see. Let me open up from the documents. That's one thing here. So you need to put this value, okay? So what was the value we have? X minus, x mean, that's the way I put it, okay? Divided by x max minus x mean, okay? Times, you need to multiply with the new max minus new mean plus new mean. So I know x minimum is 2, x max is 2, x minimum is x max is 9, x minimum is 2. The new max is 28, and the new mean is 0 plus 0. Okay, x minus 2, 7 times 28, then you get is x minus 2 times 4.
How I get 28?
28 is given in the problem, right? It's in the problem.
Oh, the range.
Yeah, that's the range. Yes.
Could you get back to the document? Okay.
Where did the 9 came from?
9 from is the maximum value in the domain. If you look at the second attribute, the maximum value is 9. The lowest value is 2. Its range is from 2 to 9, based on the data set. Okay. Once, if you get this logic, the second part will be also similar. So you have the values from here. Then you should map 1, 2, and 4, 4. This is what you are going to get. I said that you need to use N max distance. N max distance is you look at the difference of attributes and pick the maximum one. Okay. For example, let's say, let's pick this one. Let's look at here. So 28 to 8 and 7 to 16 as an example. The difference for the first attribute is 21. the difference for the second attribute is 8. We have two different, 21 and 8. For the first attribute is 21, for the second attribute it is 8. The maximum is 21, so you pick 21. Okay. That's what L max is. So that's you generate this matrix. Then you, for 7, 0, you look at the closest one. The lowest one is this one. You get positive. And then for k equal to 3, you need to find first 3. Have I made a mistake? Okay. For the second one, it's 8. 8 is also positive, so you have two positives, so it's automatically positive. You don't need to even check the third one. Third one could be negative or positive, it doesn't matter. The majority will be positive. Then for the second one, the lowest value is this one. It is negative here. And then for k equal to 3, you look at the second value. It is this one, it's negative. So you have two negatives now, you don't need to even check the third one. So it's going to be negative automatically. But doing this type of tricks, not checking all of them, will speed up your processing time during the test. Okay. I move on to the next question. So this is the estimator problem. So you need to draw the histogram. In the first range, 1 to 3, you have 3 values. In the second range, you have 1 value. In the third range, you have 1 value. In the fourth range, you have 1 value. In the last range, you have 2 values. Okay, so you see that. You need to divide it by n times h. Okay, n is 8, h is 3, so you need to divide the values by 24. That's what you get. So 2 over 24 is the last one, as an example. 3 over 24 is the first one. 1 over 24 for the middle ones. That's how we develop the histogram. So histogram basically, you need to find the count per interval and then divide by this n times h for normalization purposes. Okay. Any questions on this one? Okay. Second one is, this is the formula. Okay. So what is the difference between the naive estimator and the original histogram? Original histogram assumes that the length is, the interval is fixed ahead of time, 1 to 3. Why doesn't start from 2 and go up to 4, as an example? That's a question, right? Why doesn't start from 3 and go up to 6 or go up to 5? So what it does is, it's a moving window. So for any value, you should use this formula, okay? So the formula is given here. So for 3, basically, you should look at how many points you have in the neighborhood, okay? We are going to look at it, 3. My case 3. We are going to split into 2, 1.5 before 3, 1.5 after 3. So from 1.5 to 4.5. Okay, that's what we have, from 1.5 to 4.5. If you assume that 3 is in the middle point, then we have 3 points here. So it's going to be 3 divided by 24. The numerator is the same. For 8, 8 is not here, but still you can find that neighborhood. 1.5 after it, 1.5 before. This is from 6.5 to 9.5, right? If you subtract 1.5 from 8, so you are going to have only 1 point in the neighborhood, which is 9. 9 is in that neighborhood. It's going to be 1 over 24. Questions on this one?
So, like 8 is not in the data set, so does
what does it mean? What does it mean, right? If it is, is that your question?
Yeah, so no, I mean, like when 8 is not in the data set, so when I read the question, I thought like if 8 is not in the data set, so I need to add one more, like n should be equal to 9, not 8.
Okay. So what this does is actually, does not need to be in the data set. Okay? What you do is, you ask this question, what is the density around 8? Is it a dense area or non-dense area? That's the question that we are finding. So the answer is, if I look at these numbers, so the area around 3 is denser than the area around 8. So that's what I get from here. Okay. So the last one is K-nearest neighbor estimator. Okay, so this is one of the things I mentioned. So in this one, the numerator is constant, which is K, which is 3. In this case, I am looking at third neighbor. The denominator is changing. The changing part is this one, dk. dk is the distance to the third neighbor. Okay, basically. For each point, you do that. For 3, what is the distance to the third neighbor? So 2, 4, and 1. 1 is the third closest neighbor. The distance is 2. So I'm going to have 3 divided by 2 times 8, 8 number of points, times 2. So this is the distance. For 8, the closest neighbor is 9. The second closest is 10. Third closest is 4. Okay? You have 3 divided by 2 times 8 times 4, and so on. This is what you get. So based on this, still, this says that this area around 3 is a little bit denser than the area around 8. So this is another way to measure it. Question?
The dk of
dk is the distance to the kth nearest neighbor. dk is the distance to the kth nearest neighbor. For 3, the 3 neighbors are 1, 2, and 4. These are the 3 closest neighbors. The third closest neighbor is 1, so the distance is 2.
I didn't get it.
So what are the neighbors of 3? So I have looked at the first closest data is 4. Right here, the closest data for 3 is 4. What is the second closest data?
2.
2. What is the third closest data to 3? 1. Okay, what is the distance here? 2. So you are using this distance as dk.
We're using the minimum distance.
Maximum.
So
not maximum.
3
Oh.
minus 1.
It's
Like-
kaif.
3 minus 1. What do you mean?
The one, how do you consider 1 over 2 or 4? The farthest one.
It's the third.
Farthest.
Farthest one, I look at the distances. The distance is 1 here. The distance is 1 here. I need to find 3 closest neighbors. So the distance from 3 to 4 is 1. 3 to 2 is 1. 3 to 1 is 2. So what is your question?
Yeah, I think the formula is just new to me. I don't think I've seen it before.
If k equals to 3, then that.
So this is D1, this is D2, or D1, D2 is the same as this is D3, because that's the third closest neighbor. Does it make sense? Another question. Question 6, provide brief answers, okay, for this one. So forward selection and back elimination always provide the same outputs, okay. So I want explanations for this type of question. Firstly, forward selection and backward elimination, they are greedy algorithm. Greedy algorithm means at a point, based on the current information, it makes the best choice based on that condition, okay? So it makes the best choice locally, but that local choice may not be global best, okay? Since we are starting from forward, picking one feature at a time, that's one way. The other one is eliminating attributes, picking up all attributes and eliminating one at a time. They may not meet at the same point. Okay, so there is no guarantee that they are going to meet, because they are just trying to optimize locally. They are not trying to optimize globally. Okay, that's the first answer. Second one is if we increase the PCA components, will your clustering better if you are using clustering based on PCA? No, the answer is no. Firstly, what is the purpose of PCA? PCA tries to represent the complete data with fewer number of features, right? In a new domain. So it's not the actual domain. So more features do not always bring information. That's one thing that we know. More features may not always bring more information and could impact negatively due to distances. Because if you increase the number of components, then you are going to have a higher dimensionality. And in the higher dimension, then the distances may make little sense in very high dimensions. So PCA with maximum may not always work as we expect.
Can I take a picture of it?
No, write it.
Okay.
It's better if you learn it. Okay, should I move on to the C?
No.
No?
Can you give an example on B, please?
I mean, how can I give an example? It's a little bit abstract.
Oh, is it?
Yeah. What it means is, in a higher dimension, you think about Euclidean distance, okay? So the data points will be far from each other, okay? Yes, if you have 2 dimensions, the Euclidean distance makes sense. If you have 3 dimensions, it makes sense. 4 dimensions makes sense. If you have 1,000 dimensions, then it is in a 1,000 dimensional space, okay? The data points are in a 1-dimensional space. And most likely, they are going to be far from each other. All points are far from each other, okay? Then the distances are not comparable anymore. So what is the distance from point A to point B? 12,000, okay? What is distance between point A to point C? 12,002, okay? In that high dimension space, those numbers may not make sense. That's where the problem is coming from. And there's also a relevancy of features. Some features are not relevant. This is our observation, so this is a little bit of subjective explanation. If the features are not relevant, they are typically confusing the model. Okay, so avoiding those features is better. And if you remember, I am going. This is PCA. So where is PCA? So this is an example that I have shown in the class. Look at the PCA 1, 3, 5, 7 components. From PCA 1 to PCA 3, it goes down. Then from up to PCA 5, it goes up again. Okay? And then PCA 7, it goes down again. Probably there is one change in the accuracy. One data is classified correctly and classified incorrectly. So you can see that it doesn't always improve having more. That's one case. This is from the this BCW disk, this cancer data from the UCI dataset. And the first one is, this is the Bayes inaccuracy. So PCA1 gives better with just one feature, better than Bayes inaccuracy.
Last line. One line.
So as you write, I am going to continue with the other one. So the other one is easy. That's something. So what is the first expression here? The first expression says that when you project the data on a vector, so you have multiple vectors with different directions, you want to maximize the variance, so data open up so that they could be separated easily. Okay, so that's related with the direction of the vector. Vector means direction. Okay, and you need to maximize the variance over there. The second expression here is, to be fair to each vector, you normalize, you assume that the distance of all of them are the same. I set it just to 1. You could also set it to 2, 4, 5, anything you like, but 1 is simple, so that's why we set it to 1. Okay. So this is the last question. This is cluster validity. So you have seen reconstruction error in the first problem, right? So you can compare two clusterings, whether one is better than the other based on comparison of the reconstruction errors. This one is for class validity. As soon as you have classes, how can you determine whether your clustering is good if you know that the classes are already available? Okay, so this is the way you look at it. So if you look at this, so I'm going to label them rows P1, P2, P3, P4, P5, P6, okay? P1, P2, P3, P4, P5, P6. So when you see 1 here, P1 and P1 are in the same cluster. P1 and P2 are in the same cluster, okay? You say, I see that P1 and P1 and P2 are in the same clusters. Okay, I see that. P1 and P2 are in the same clusters. Same thing, because it's symmetric. If P1 and P2 are in the same cluster, P2 and P1 are in the same cluster as well. That's why it's a symmetric cluster. In the middle here, P3 and P3, P3 and P4 and P3 and P5. So P3, P4 and P5 are in the same clusters. And P6 is by itself. Okay? This is the cluster. So P1 and P2 are in the same cluster. There's nothing else in the cluster of P6. Now check the clusters. What does the classes say? Classes says that P1, let me put it in P1, P2, P3, P4, P5, P6. P1 and P6 are in the same classes. That's what we have. P1 and P6 are in the same class. And then here, look at here, P2 and P3. P1, P2, P3, P4, P5, P6. P2 and P3 are in the same classes. P4 and P5 are in the same classes. Okay. So this is what we have. This is what we obtain. This is the correct result. This is correct. Okay, this is ground truth. This is our result. So this is the first part of the problem. Okay. So first part is P1, P2 is in one cluster, P3, P4, P5 is in the second cluster, P6 in the third cluster. Now the question is, how good is this clustering given this? How good is your clustering? You know the classes now. How good is your clustering? For that purpose, this is what you do. Okay? Let me use a different color. It's a symmetric matrix. typically we look at the upper triangle. We can also look at the bottom triangle. So 1 means the data points are in the same class. The P1, P2 assignment is correct, for example, right? P1, P2 means they are in the same cluster. But here, P1, P2, they are not in the same class, okay? P1, let me also mark here. So I'm going to explain, pick one of them, so that it makes sense. So this is 0, this is 1. So my result says that P1, P2 are in the same cluster, but actually P1, P2 are in different classes. Okay, you see that, different classes. So there is a problem here. I put them in the same cluster, but they're in different classes. So what do you see here? 1 from here, 0 from here. What is this? 1, 0. You remember Jacquard? 1, 0. Let's look at the second one. I have 0, 0, 0, 0. 0, 0, 0, 0. 0, 0, 0, 0, 0, 1. This is 0, 1. So you count them. How many 1 ones? How many 0 zeros? How many 0 ones? How many 1 zeros do you have? If you count it, this is you get, there are 9 0 zeros here, 2 0 ones here, 1 1 0, I mean 3 1 zeros here, and then 1 1 here. Only one of them is matching actually. This is very surprising actually. And the one that is matching, I believe, is this one. There's a different color. So this one is, I believe, so this one is matching. So this is the only one we were able to, do it properly. So P4 and P4, P5, they were put into the same cluster and classes. So that's the only good achievement we have. So you know the Jacquard formula now. It is F11 divided by F01 plus F10 plus F11, 1 over 6. So this is in the slides. No, yet this is inside. This is also in sample questions. This was there. All questions, I think there is a similar question in the sample questions, yes.
There are two positions that F11, like they both equal to 1.
Have I made a mistake?
Yeah, so there are two positions. There's one position at the row 5 and
Row 5?
4.
Row 5 and 4?
Row 5 and 4, yeah, that one.
This one?
Yeah.
We'll just look at the upper side or lower side of the triangle. That is under the lower side. So this is symmetric matrix. You can work on the symmetry. You are going to get the same result. But you need to work on both sides in that case. Okay? So you need to work, in that case, this side as well. Okay?
But the symmetry between
Yeah. So you are going to get the same result if you work on both sides of the diagonal. You are going to get the same results. The one thing that what you are going to get here is that this one number will be 2, the bottom side will be 12. That's what you are going to have if you use both sides of the triangle.
So what do you mean by explain?
Which?
I used both the whole cluster.
Okay.
The whole cluster, but you wrote explain.
So here's the thing, what it means. If your answer is incorrect, and I cannot make sense of how you got those numbers in there, then you gave me something like 1 over 6. But of course you don't give 1 over 6, you give me something like 4 over 14, okay? I don't know what 14 is, okay? If you explain it, if you don't have that explanation, then...
I have the formula.
You have the formula, but what are they? I mean, we may discuss it. If it is, I might have missed your answer. In that case, you need to return your paper back to me, and then we can discuss during my office hours. Okay? So that's not a big problem. Yes. No, don't ask any question about your answer. If you have a question, you need to return back to me.
Yes.
Okay, just give it back to me.
So
You need to-
maybe this part you didn't check.
Yeah, maybe. It's possible.
But that's
So you need to come to my office and we're going to check it. Same. So if you have any objections, please return your paper back to me.